Hello champions, I am Chandan Biswas, and in this video we are going to learn about first law of thermodynamics. Now the first law of thermodynamics is also known as the law of conservation of energy, which can easily be summarized as the total amount of energy in the entire universe is constant. Now if you want to look at it mathematically, the first law of thermodynamics is written as delta U equals Q plus W. Now what is delta U? Delta U is the change in internal energy of any system. Q is the heat given or taken by a system, and W is the work done on or by the system. We have to put these values with appropriate signs in order to calculate the net energy change or see that if this formula is valid or not. So simplified form is this. Now let's talk about each of these terms one by one. The first term is delta U. Delta U is also known as internal energy change. Now internal energy change is strictly a function of temperature only, which means that nothing else will change the total internal energy of any system. However, this is an extensive quantity, which means that it will depend on the size of system or the mass of system. For an ideal gas system, delta U is written as F by 2 nRT, where F is the degree of freedom, N is the number of moles, R is the universal gas constant, and delta T is the change in temperature in Kelvin scale. Now what is F here? Because rest of the terms we have known already, but what is F? F is the degree of freedom, and if degree of freedom can be defined for different gases in these formats. So F can be taken as 3 for any monoatomic gases. Monoatomic gases can be like helium, neon, argon, xenon, like that. If it is a diatomic gas, which is basically like O2, N2, so therefore in this case we can take the degree of freedom F as 5. So in this category the examples will be O2, N2, F2, H2 and so on. And lastly we have F, which is equal to 6 for any non-linear and multi-atomic gases. For example, we have CH4, we have NH3. For those gases we have to take F value equal to 6. So substituting this value for any ideal gas, we can easily calculate the value of delta U. The next term in this formula is Q. Q is the heat formula, and now heat is a path function, which means that it depends on how any system is achieving any particular state. So Q can be calculated for any different system in multiple ways. For example, in the first one we have Q equals the substitute for heat, and Q is calculated as C delta T. So in this case C is nothing but the total heat capacity of a system, and so therefore if any system has any specific total heat capacity C given, we can easily use that formula to calculate the total heat given or absorbed from a system. Another way to do the same is by specific heat capacity, which is denoted as S. So here we can see that Q will be written as ms delta T. So ms means M is the mass of the system, S is the specific heat capacity, which is usually given in joule per Kelvin per gram or joule per Kelvin per degree Celsius or something like that. So this formula can be used for any system mass if it is given. And the third one is Q equal to NCV delta T. So in CV delta T means CV is here stands for any molar heat capacity. So this is a constant for any given gas, CV, and another formula is written as Q equal to NCP delta T, which is another molar heat capacity here. So CV stands for the molar heat capacity for any constant volume, and CP stands for heat capacity at a constant pressure. So these are the ways by which we can evaluate Q for any given system. The third one is, however, is W, which is the work done. Now work done can be calculated in two different ways. One is a reversible isothermal process, and another one is irreversible isothermal process. So according to reversible isothermal process, the W can be written as minus nRT ln V2 upon V1, and in that case we can also use minus nRT ln P1 upon P2. Or in this case, if we have irreversible process, in which means that the pressure is not constant, so the work done will be written as minus P external into delta V. Now remember this fact that W is not a state function, it is a path function, because it will also depend on the path by which any work is done. And the third one is for adiabatic processes. Work done can be written as P2 V2 minus P1 V1 upon gamma minus 1. So in this case, we can calculate the delta W for different processes, and that sums up everything about the first law of thermodynamics. So that's it. I'll see you in the next one.